Okay, now we're going to finish up on the ear and the hearing aspect of it. And then the last thing we'll do today is look at equilibrium, which is another sense located at the ear. But anyway, we've done the outer ear, we've done the middle ear. Now we're going to look at where the receptors are actually located, and that's in the part of the ear called the inner ear. And it is a pretty complicated organ structurally. Sometimes it's referred to as a labyrinth. You get that idea by just looking at it, don't you? But it's the outer part of it is bone, right? And so inside of that is a membranous tubing that pretty much follows all the same contours. And so there's an osseous labyrinth, which is the outer part, and then there's a membranous labyrinth, which on this picture is the darker blue part. And there's fluid in there. If we looked at this part of it, if we did a cross section right there, here's what you would see. So this would be the membranous labyrinth. This would be the part of the osseous labyrinth. And the fluid that you see in the brown area outside the membranous labyrinth, that's called the perilymph. And the fluid inside the membranous labyrinth is called the endolymph. Okay? So I mentioned to you that there's fluid in the inner ear. Okay, there's two fluids. There's the perilymph and the endolymph. Okay? All right, then if you look at the different areas of the inner ear, there's three parts. There's the semicircular canals, the vestibule, and the cochlea, which you can see here. The cochlea, semicircular canals, and vestibule. The most noticeable thing initially is probably the semicircular canals, but there's one, there's one, there's one. Each ear has three of those because you've got two of these inner ears in your head, right? One on each side. And this, by the way, is embedded within your temporal bone. So it's pretty complex little structure. It's like bones within a little bone within the temporal bone. But so it's very protected there. The semicircular canals have receptors for equilibrium, so we'll see that towards the end of our talk today. And then the cochlea is where the hearing receptors are, and that's this curled up, coiled part. It's kind of like a snail shell coiled up like this. And the hearing receptors are there. And then the vestibule is just in between the two. So this area right here would be referred to as the vestibule. Okay? Well, that area. Okay. So students always get confused on where's the vestibule. But it's just in between the cochlea and the semicircular canals. Okay? All right. Now, if we look more closely at the cochlea, on this picture, you can see that on this picture they've uncoiled it. Do you see that? And then you see the cross section of it does not look like the cross section of a semicircular canal, which is what that other cross section was. Remember, on the semicircular canal you had a tube within a tube, and you had perilymph out there and endolymph in there. Remember that? On the cross section of the cochlea, it looks like this. And so the inner compartment filled with endolymph is right there. And then perilymph is on either side of it. It's just weird how the membranous part positions itself in the cochleas. The hardest thing in this chapter is visualizing the cochlea. Okay? So in lab on Thursday, we're going to look at a lot of models that will help a little bit. But the cochlea does not uncoil. Okay? It actually, this whole part right here is coiled around a cone-shaped little bony structure. Just imagine that little thing it curls around being like a screw. You know how a screw has a thread on it that spirals around? Okay, the whole cochlea spirals around that. It sits on that little thread of bone, which you don't see on any of these pictures, but anyway, it's just kind of weird. The oval window, remember that's the membranous part that the stapes is connected to? All right, if you could uncoil the whole thing, you would see that the oval window actually connects to this upper compartment, like that right there, that upper compartment. Okay, so basically what's going to happen is fluid is going to move in this compartment, and it moves down to the end and then down this way, down this way, down this way. This fluid is perilymph, and it's moving, all right, and any excess movement is picked up by another window I haven't talked about that's at the lower compartment, at the proximal part of the lower compartment. It's called the round window, and its purpose is simply to catch excess movement so it won't be bouncing around all the time. Okay, but as the fluid moves down the end, it's also this fluid move. Let me get rid of this. Didn't red. As the fluid starts moving here because of the vibration of the stapes, it triggers this little membrane to start moving up and down. Okay, and as that membrane moves, do you see how it gets endolymph in there to start moving? And then that triggers the bottom membrane to move. And do you notice there's something sitting on that bottom membrane? And that is your hearing organ. And it spirals all the way around this because it's sitting on that lower membrane. So it's all along the base right there, all the way down to the end. So it spirals along. And as this fluid, watch, this is a difficult concept to catch. As this fluid is moving down towards the end, it's causing this membrane to vibrate, and that causes the fluid in there to move, which causes the base, this bottom membrane, to vibrate. All right, and then in a minute, I'm going to show, right now, I'm going to go to a picture that shows that part more magnified. There you see it a little bit. Like here's a slice of the cochlea. Here you see it on a sectioned view. So do you see the three compartments? 1, 2, 3. And then here as it spirals around the three compartments, 1, 2, 3. It goes to this side, the three compartments, 1, 2, 3. See that? How it's spiraling around? All right. And then here's one of those right here. Okay, and so here's the middle compartment filled with endolymph, perilymph, perilymph. And do you see this complex little structure sitting on that membrane? That's your hearing organ. And it's called the organ of Corti, or the spiral organ, because it spirals around that lower membrane. And if we looked at that area in this box more closely, I'm going to come back to all these words. Here's the area. Look at it more closely. All right, there is the hearing organ called organ of Corti. And do you see this, what on this picture looks like a blue membrane above it? That's a membrane that goes about halfway out that middle compartment. And it's the only thing in here that never moves. It stays still. And when it stays still, the organ of Corti can move up against it. And at the edge of that, those cells, do you see, they're called hair cells. It's like little cilia there. And if they get pushed up, look, they're going to bend. And if they bend enough, that's going to trigger an impulse to go along that little nerve, or that little neuron, to the cochlear part of the vestibulocochlear nerve. Remember, that's one of your cranial nerves. It's going to send impulses to the hearing part of the brain. What is that? Okay. Okay. So this constant, the initial movement of the oval window, I'm going to back up several pictures here. Get rid of all this green. Okay. All right, so here, where do they show the oval window? Yes. Okay, here's, like, imagine the stapes is connecting right there, right here. Okay, and so that sets up fluid movement. See how that fluid movement goes there? And then it causes this membrane to vibrate, which causes the endolymph to vibrate, which causes the lower membrane to vibrate, and that's going to push it up against that rigid one. Okay? Wherever it causes, wherever that vibration movement or the liquid movement channels through, those are the receptors that are going to get activated. Okay? And that's going to cause you to hear from different frequencies. Okay, and then any excess movement is absorbed by the round window. Okay, So all these little areas are going to have a name. The action is actually quite simple, but you've just got to get the terminology down. Ooh, that's not good. Okay. All right, and so if we looked at all these different compartments of the cochlea, I'm going to draw it big. Like there's the cochlea, and then it's sort of somewhat like that. Now it can be a mirror image of that if it's spiraling on the other side, But you've got, remember, perilymph, endolymph, perilymph. Okay. This upper compartment right here is called the scala vestibuli. The middle compartment, and all this is written down somewhere through all of this, like scala vestibuli, you see it right there. The middle compartment is the cochlear duct, and it's filled with endolymph. And then the lower compartment right here is the scala tympani. So you got to name the compartments. But then we also are going to name the membranes, and they may be on the next slide. But this membrane right here is called the vestibular membrane. And the lower one is called the basilar membrane. And the organ of Corti sits on the basilar membrane. Okay, so I'll draw it in red. Like there's a little. I'll just put it right here. Organ of Corti is right there. And then jutting part way out in the cochlear duct is the tectorial membrane. And this is the only thing that doesn't move. Membrane. Okay? And you can see that labeled on some other pictures. Okay, so you can see it here. Sorry. Well, my smart board's not working like it needs to. There. That helps. I don't know why I can't get that blue off. That's weird. All right. Anyway, so you can see what is the name of that duct, that area. Scala vestibuli, scala tympani, cochlear duct. And then the three membranes are the vestibular membrane. This blue is the tectorial membrane, and then the one that the organ of Corti sits on is the basilar membrane. Okay? And then this is the organ of Corti right there. Okay? The hardest thing, it may not be hard to you at all. I just know for myself, when I first started teaching the ear, this was a hard concept for me to get, and then for the students. But the hardest part is that you're seeing a flat section, but you got to remember this whole area goes around that little thing that looks like a screw. Actually, it's a little piece of bone that looks like a screw with threads on it, and this whole thing spirals around that. Okay. All right, here you can see under the microscope, this would be the basilar membrane. And so here's the scala tympani, so perilymph would be here, and this part of the cochlear duct. So it doesn't show the vestibular membrane above it. Okay, but there's the organ of Corti. Look at that. You can barely see the little cilia, but you really can see the tectorial membrane. Okay, and then if you were looking down on the cochlear duct from the top, I guess without this, this is what you see, the enhanced picture on the right. I don't know if I'm going to ever get this blue line. Oh, there it goes. Okay, I'm getting it off now. That is so strange. All right. But you can see the little cilia. Okay. All right. Now, I love this picture. This kind of puts it in perspective. This, if you could stretch the whole thing out, and here you see a vibration of the tympanic membrane. It causes the malleus, the incus, and the stapes to start moving, which presses on the oval window, which sets up this fluid movement in the scala vestibuli. Okay? And then that would trigger, as it moves on down, then ultimately it's going to cause this to move in a certain area. That'd be vestibular membrane, which causes endolymph there to move, which causes the basilar membrane and the organ of Corti to move up against. This is showing that tectoral membrane if you're seeing it go out. All right. And then the movement is picked up down here and absorbed at the round window. What I like about this view, though, it's not necessarily test material, but it's interesting. You know how you have sound waves resulting from different pitches? Have y'all ever studied the physics of sound? A sound wave, if it's a high-pitched sound, watch me, the sound wave is real short, like this. If it's a low note, like a low-pitched sound, the sound wave is a lot longer. Okay, long sound waves, when they cause this to move, it triggers it to go way here before it activates receptors. And that gives you the sensation of the low note. But if it's a high-pitched sound wave, or a sound causing a high-pitched sound wave, all right, it fizzles through a lot earlier. And so the receptors for the high notes are at the proximal end of this. And that's what these CPS is. That's cycles per second. You know how many sound waves per second. It's interesting. But if you were in audiology, you would learn more detail on that. Sometimes people have hearing loss because they may have lost some receptors. Like some people have a hearing loss for just the low-pitched sounds or the high-pitched sounds. Maybe they've lost receptors here but not there. It could be because of repeated exposure through the years to loud sounds. It causes those cilia, those cells, just to get crushed all the time. And it may cause so much damage it affects the neurons that they're connected to. Sometimes it's a problem with the bones being too rigid. It may be a problem with the movement of the tympanic membrane. It could be a problem with the nerve, the cochlear part of the vestibulocochlear nerve. So, there's a lot of things that can be involved in hearing loss. But a whole lot of people suffer from hearing loss. Okay, y'all have any questions on hearing? Read. Go on YouTube and get some videos of the mechanics of hearing, and that will help you visualize this a lot more. Okay, we're going to finish up today looking at the fourth sense of equilibrium. And the receptors for equilibrium are also located in the ear. They're just not in the cochlea. They're in the other parts of that inner ear. We all know we have a sense of equilibrium or balance, but you may not realize you have two kinds of equilibrium. There's static equilibrium and there's dynamic equilibrium. Static equilibrium is what's keeping you in balance when your head's not moving around. So, for example, it's early this morning, and I can tell some of y'all just want to do this. You want to nod off. All right, you're pretty much motionless, aren't you? And if your head nods off, you know how you jerk up? All right, that's your static equilibrium. And so it helps keep your balance. You've got to have muscles contracting to hold yourself upright. And your sense of equilibrium helps with which muscles need to be contracted to do that. The organs for static equilibrium are located within the vestibule of the inner ear. Okay, vestibule is that area between the semicircular canals and the cochlea. Okay, dynamic equilibrium keeps your balance when your body is moving around. Okay, and the organs for dynamic equilibrium are found in the semicircular canals. So we're going to take each of these one at a time, starting with the static equilibrium. On your test, hint, coming up next week, if I ask you what is the name for the organ of static equilibrium, you're going to say macula. That's the name for the organs of static equilibrium, and you've got two of these in each ear. Okay, they're located in the vestibule. Okay, now this picture is very difficult to visualize, but what I want you to look at is the purple, the membranous part. Okay, here is the vestibule, is this area, and within the vestibule there are two purple sacs. Can you see two purple sacs? One is called a utricle, like this is one of them, and then this one is the other. It's the saccule, the utricle and the saccule. That may be a little easier to see on some other pictures. I want to back up quite a bit. I'll come back to this. I think I saw it better early on in the chapter. That's the same picture, isn't it? Never mind then. Okay, just trust me. There are two sacs. There's a utricle and a saccule, and those are the membranous sacs filled with what fluid? What's the middle fluid? Endolymph. Okay. In the wall of the utricle and the saccule is, you see that green rounded area? That's a macula. And so the organ for static equilibrium, one of them is in the wall of the utricle, the other is in the wall of the saccule, and both of them are in the vestibule of each inner ear. Okay? Yeah, it just lines the wall of the saccule and the utricle. Okay. Part of that, yes, is that the same when a baby is born and it takes them several months to have control of their head. Most of that is just their nervous system isn't developed enough to have that good control of the muscles. But all right, but what you're seeing on this picture is a detailed view of what a macula looks like. Okay, and it is one of the coolest organs. See how it's in the wall? So there's epithelial. So there's the epithelium, the highlighted in red there. And then do you see how the receptor cells are embedded in that? And do you see how they're called hair cells. They have these cilia-like structures on them. But do you see how the cilia is embedded? They're embedded in this gelatinous mass that has little crystals inside of it. You see that? These crystals are crystals of calcium carbonate, and they're called otoliths. Otoliths. It's calcium carbonate. Kind of like chalk. But anyway, it's really interesting when, look at this picture at the bottom, when her head's upright, this is what the macula looks like. But if she starts moving her head down, if she nods off, look at that. Do you see how gravity pulls on the otoliths? And because they're within that gelatinous mass, that whole mass moves. And what happens to the cilia? They bend. So these are just mechanoreceptors. And if they bend enough, that's going to trigger an action potential to go on the vestibular part of the vestibulocochlear nerve to the balance centers of the brain. It's going to tell her muscles back here to contract, and she'll pull her head back up. Okay? Interesting, isn't it? And it's simply just gravity pulling on that. So the mechanics of it are super simple, but there's a lot of terminology. What is static equilibrium? Keeps your balance during motionless periods. What's the name of the organ? Macula. Where is it located? In the wall of a utricle and a saccule that's located in the vestibule of an inner ear. Okay? And what does it look like? The hair cells, cilia, are embedded in a gelatinous mass that has crystals of calcium carbonate or otoliths inside it. They're little crystals. And when the head moves, gravity pulls on all of it and causes the cilia to bend, and that triggers the action potential. Okay. Y'all familiar with crawfish? Crawfish have an organ it's not exactly like this, but it helps them keep their balance and know when they're upside down and right side up. A crawfish does not have a very big brain. In fact, it's really tiny. Um, if you've ever dissected a crawfish, you might remember some of this. But you know how crawfish have all these little feeding appendages around their mouths? And so they're constantly filtering through the sand or the dirt that they live in, the mud, and getting food in their mouths. And then those little sand particles, if any get in the mouth, they are channeled not into his stomach, but into a space above his mouth, which is not, I mean, his brain takes up a tiny little area, but most of that's just empty space. It has this sand. No, I'm serious. Has sand there. And as long as that sand is sitting on the bottom of that cavity, his brain realizes that he's right side up. But if he gets flipped over, he's not, his brain isn't developed enough to know from his sense of vision that he's upside down. What happens is those little sand grains get to the other side of that cavity. And I don't know if there's cilia up there or it's just a lack of the presence of it on the cilia at the bottom. But anyway, his brain realizes he's upside down, and so he flips over. There have been experiments done with those little crawfish, and they put them in a little tank where instead of grains of sand, they have iron filings where his food is. And so he's filtering through that. Little iron filings get into that chamber, and then they'll take a magnet, a big powerful magnet, and go across the top of his head. It doesn't hurt him. Goes across the top of his head, so the iron filings go up to the top, and he turns upside down because his brain thinks he's upside down when the iron filings go up there. Anyway, it's kind of like this. It's a gravity thing, but that's their organ of balance to keep them right side up. Are cockroaches smarter than crawfish? That's a real good question, and I have no idea. Probably. Yeah. Anyway. Yeah, that's what you'll remember about this chapter, isn't it? The crawfish. Yep. Okay. Dynamic equilibrium keeps your balance when your head is moving around. And the organs for them, the organs are located in the semicircular canals. The name of the organ is a crista ampularis. That's the organ's name. And its location is at the base of each semicircular canal, also within that membranous part. And that swollen area, I don't care that you know the name of that, but just know that they're in the semicircular canals. They're in like there's one in there, there's one in there, and there's one in there. See that little swollen area? That's where they are, the crista ampularis. Crista ampularis. Okay, now this is how they work. Okay, see, up on this little picture, there's a crista ampularis. There's one, there's one. They're at the base of each semicircular canal. Have you noticed that the semicircular canals are at 3 different planes that are at right angles to each other? Okay. If you look at the organ, the crista ampularis, this big picture that you see, it's got little hairs or cilia, kind of fused cilia, that extend into another gelatinous mass. But this mass is firmer and it's kind of dome-shaped. It's referred to as the cupula. You ever heard of that word, cupula? It's an architectural structure. There is one called a cupula, like the dome on the top of the state capitol is referred to. That dome structure is a cupula. Okay, well, see, here's a cupula in the inner ear. And the cilia, they're long, real thick cilia, extend into that. Because this is all within the membranous labyrinth, so there's endolymph all around this. Okay, and watch at this bottom right picture. All right, here she is. Her head is still, and now when her head turns, do you see how it sets up a fluid motion? It's kind of a centrifugal force thing. Think about this. If you're spinning around, it's gonna, when you stop spinning, the fluid in there is gonna keep going, isn't it? And do you see how it's going to pull along that gelatinous mass, the cupula? And if it does it enough, what happens to the cilia? They bend. So it's, again, mechanoreceptors. And depending on which of the semicircular canals that bending is occurring, that tells your brain how to keep yourself from falling over, which muscles to contract. Okay. So when your head is upright and it's spinning around, one of these will be activated. But if your head's down a little bit and you're spinning, it activates other ones. And it's just because they're at different angles. Okay. All right, so the design of them is pretty simple for equilibrium, but there's just a lot of words that go to all the parts. So your first step is to get the terminology down. And once you do that, you're not so confused about the action of everything, because you have to use those words. Okay. All right. The last part of this chapter is vision, and we will cover that in our next lecture.